Today, we're diving into one of the most perplexing and fascinating mysteries in all of science. It's a story that involves cosmic titans and subatomic rebels, our tale of two brilliant theories that describe our universe with incredible accuracy, but absolutely refuse to play nice with each other. We're talking, of course, about the epic showdown between gravity and quantum mechanics. And why their disagreement means, in a very fundamental sense, our understanding of physics is currently broken. Now, that might sound dramatic, and it is. For decades, physicists have been trying to unify these two pillars of modern physics, to find a single, elegant theory that can explain everything. But so far, no luck. It's like having two halves of a perfect jigsaw puzzle, except they were made by different manufacturers and have completely incompatible edges. So, what exactly is the problem? Why can't we just stick them together? To understand the fight, we first need to appreciate the individual strengths and triumphs of our two contenders. Let's start with the big one, gravity. Or, more precisely, Albert Einstein's general theory of relativity. Published in 1915, this theory completely redefined our understanding of gravity. Isaac Newton described gravity as a force pulling objects together. Einstein, the genius that he was, said, "Hold my beer, Isaac." Einstein showed us that gravity isn't a force at all. Instead, massive objects like planets and stars warp the very fabric of spacetime around them, much like a bowling ball placed on a stretched rubber sheet creates a dip. Other objects, like marbles, don't so much get pulled by the bowling ball as they simply follow the curves in the sheet. They're following the geometry of spacetime. General Relativity is an incredible success story. It accurately predicts the orbits of planets, explains the bending of starlight around massive objects, and even led to the prediction of black holes and gravitational waves, phenomena we've now directly observed. It's our ultimate guide to the cosmos on the largest scales. It is, in a word, beautiful. Now, let's pivot to the other corner, quantum mechanics. If general relativity handles the cosmic ballet of stars and galaxies, quantum mechanics is the chaotic, unpredictable, and utterly mind-bending dance of the subatomic world. It governs particles like electrons, quarks, and photons, the fundamental building blocks of everything. Forget deterministic paths, in the quantum realm, things are fuzzy. Particles can be in multiple places at once, superposition, they can instantly influence each other no matter the distance, entanglement, and they only decide on a state when observed. It gave us lasers, transistors, and every piece of modern technology from your phone to medical imaging. Quantum mechanics, combined with special relativity, forms what we call quantum field theory, our most successful framework for describing the other three fundamental forces: electromagnetism, the strong nuclear force, and the weak nuclear force. It is, in a word, precise. So, we have general relativity, beautiful, deterministic, describing gravity on large scales, and quantum mechanics, precise, probabilistic, describing the other forces on small scales. Both are incredibly accurate within their own domains. But here's the rub: they use completely different languages, different mathematical frameworks, and fundamentally different assumptions about how reality works. General relativity treats space-time as a smooth, continuous fabric. Quantum mechanics, however, tells us that everything at its most fundamental level is discrete, quantized. Energy, momentum, even time and space themselves, are thought to come in tiny, indivisible packets, or quanta. Imagine trying to describe the ocean. General relativity is like watching the smooth, continuous waves from a distance. Quantum mechanics is like trying to describe the individual, discrete water molecules that make up those waves. When you zoom in on Einstein's smooth spacetime to the incredibly tiny, Planck scale, quantum effects should dominate. But when you try to apply the math of general relativity to these quantum scales, it breaks down. You get infinities, nonsense answers. The equations just don't work together. This problem isn't just an academic inconvenience. There are places in the universe where both gravity and quantum mechanics are incredibly important simultaneously. Think about the heart of a black hole, a singularity where matter is crushed to an infinitesimally small point, creating an immense gravitational field. Or think about the very first moments of the Big Bang, when the entire universe was smaller than an atom. In these extreme environments, our physics pipeline completely clogs up. We can't properly describe what's happening because our two best theories are at war. It's like having a map for North America and a map for Europe, but no map for the Atlantic Ocean in between. We're missing the crucial bridge. This is why physicists say physics is broken. Not broken in the sense that our theories are wrong, they're incredibly right in their respective domains, but broken in the sense that they're incomplete. They don't give us the full picture. So, what are the leading contenders in the quest to unify gravity and quantum mechanics? The holy grail of a theory of everything. One of the most famous is string theory. String theory proposes that the fundamental building blocks of the universe aren't point-like particles, but tiny, one-dimensional vibrating strings. Different vibration patterns of these strings give rise to different particles: electrons, photons, quarks, and crucially, the graviton, the hypothetical quantum particle that mediates gravity. String theory also predicts extra spatial dimensions beyond the three we experience, curled up so small we can't detect them. It's a mathematically elegant framework, but so far, experimentally unverified. Where string theory tries to quantize matter, loop quantum gravity tries to quantize spacetime itself. It suggests that space and time are not continuous but are made up of tiny, discrete, loops, or atoms, of spacetime, forming a fabric at the Planck scale. This approach inherently builds quantum mechanics into the structure of spacetime, potentially providing a way to describe gravity at the smallest scales. Beyond these two giants, there are other fascinating ideas: causal set theory, emergent gravity, twistor theory. Each offers a unique perspective on how to mend the broken bridge between quantum and gravity. The challenge is immense, requiring breakthroughs in mathematics, experimental physics, and conceptual understanding. The hunt for quantum gravity isn't just about elegant equations, it's about understanding the very nature of reality. What happens at the heart of a black hole? What was the true beginning of our universe? Does space-time truly pixelate at the smallest scales? These are questions that transcend our current scientific capabilities, demanding a new, unified understanding. What's clear is that we need something radical. Something that perhaps redefines our understanding of space, time, energy, and matter in ways we can barely conceive of now. It might require entirely new physics, or a brilliant conceptual shift that makes everything click into place. The fact that our best theories contradict each other at their extremes isn't a sign of failure, it's a signpost. It tells us precisely where the next great revolution in physics needs to happen. It's an invitation to explore the unknown, to push the boundaries of human knowledge further than ever before. This brokenness, this fundamental disconnect, is perhaps the most exciting challenge in all of science. And who knows, maybe the person who finally solves it is watching this video right now. What are your thoughts on this epic physics dilemma? Do you think string theory holds the answer, or is loop quantum gravity closer to the truth? Or perhaps something entirely new? Let me know in the comments below. If you enjoyed this deep dive into the mysteries of the universe, please hit that like button, subscribe for more science content, and ring that notification bell so you don't miss our next video. Thanks for watching, and I'll see you in the next one.